Okay, so today we're going to talk about angle-angle similarity, side-side-side similarity, and side-angle-side similarity. So we're using these notes from the content library, and then some of them, like these proofs that are later on, we will do together when we're back in class. So for the first one, AA similarity theorem. So if we have two angles of one triangle congruent to two angles of another triangle, then the two triangles are going to be similar. And they're not going to be congruent, they are going to be similar. So you can see over here, this is supposed to be a Z. So we have triangle ABC, so I know that angle A and angle Z are congruent, and angle C and angle X are congruent. So since I have two angles that are congruent, then I know triangle ABC in that order is similar to ZYX. So notice that the angles that are congruent correspond, and so you can see the order matters. So looking at this first example, are the two triangles similar? Well, I know for sure I have two 90-degree angles, so that tells me one angle, then I have a 30 and a 60. Now I know that angle M here would have to be equal to 60 degrees and angle X would have to be 30 degrees. So I do in fact have two angles. I have all three really. So I can say that triangle PNM would be similar to PNM. I would go XZY. All right. Now, if I look at example 2, we want to show that triangle ABE, so this little triangle here, so I'll highlight that in green, is similar to ACD. So that's this big one out here. Now, I see right away that I have 52 degrees here, 52 degrees here. That tells me that they're congruent. Do you see another angle that's congruent? Now, you might say D and E. However, we don't know necessarily for sure, but we do know that since these are corresponding angles, that must mean that my lines are parallel. So these guys must be congruent. But I also see that angle A is used in both of my triangles. I have angle A here for angle AEB, triangle AEB, and then I also have A is the same in ADC. So really, I do have those similar by angle-angle similarity. And again, we can only say these two angles D and E are congruent because corresponding angles, that means I have parallel lines. And since I have parallel lines, I have corresponding angles are congruent. So go ahead, pause the video, and try to do examples 3 and 4 on your own. Okay, so you should see in this first one that the triangles are similar. I have vertical angles here. So angle ILE is congruent to SLY. And then I'm also told that angle E and angle Y are both 35 degrees. So I can say that my two triangles are in fact similar. Triangle EIL is similar to triangle YSL. When I look over here, I see that I kind of drew them separately down here. Both of them have 90-degree angles. They both share angle C. So that would be triangle CDE is similar to CAB. So then I used what I knew for the proportions is that 36 corresponds to 12, so X must correspond to 5. I reduced 36 over 12 to 3 over 1, because if I reduce them both by 12, so 3 over 1 equals X over 5, so AB has to be 15. Okay, so we're going to hold off on these proofs for right now. We'll come back and do those in a little bit. So that's our first similarity theorem, is that all I need is two angles to be congruent. And so take a second and think about why you wouldn't need that third angle. Now we could say angle-angle-angle similarity. However, if I know that two angles are congruent in two separate triangles, then I know by default that that last angle has to be true. So if I add these two up and subtract from 180, I'm left with B. If I add these two up and subtract from 180, I'm left with Y, so those two must be the same. So we only need two angles for sure to say that the triangles are similar. If you have all three, that's great, but you just need two. Okay, so side-side-side similarity. So if the side lengths of two triangles are blank, then the triangles are similar. So if the corresponding side lengths of the two triangles are proportional, then the two triangles are similar. So you can see over here, if AB over DE, so we're saying here, if this guy here corresponds to this one, so AB to DE, if they're corresponding, if BC corresponds to EF, and then if AC corresponds to DF, then I know that the triangles are in fact similar. So if I look here, I want to know, are either triangle MNP, so this little one here, or XYZ similar to triangle ABC? So what I would need to do is to relate the corresponding pieces. Now I'm going to start by looking at lengths. So chances are the smaller one is going to compare to the smaller one. So this is supposed to be ABC. So if 18 over 24, if that fraction is equal to 27 over 36, and if that's equal to 39 over 56, then I know for sure that I have similar triangles. So let's see what we have here. So 18 over 24, those both reduce. 27 over 36 reduces, then we can check to see if 39 over 56 reduces. So in my calculator, I went ahead and put in 18 over 34, and that reduced to, as a decimal, 0.75. 27 over 36, that reduced to 0.75, so we're good so far. But then 39 over 56, if I type that into my calculator, I get a decimal of 0.696, which is not equal. So we know that triangle ABC is not similar to triangle, let's see, we did ABC, so that would be XZY. Okay, so we know for sure that it's not similar. So now let's compare with the middle one. So you go ahead and try that one. So as you can see my work over here, I compared the short side, so 18 and 12, then the medium size, 27 and 18, and then 39 and 26. And when I put in my calculator, I got 1.5 as decimals. You could also find fractions. And so 1.5, and I see that my two triangles ABC is in fact similar to PNM. Now over here, let's look at these two down here. So for example 2, I want to show that all these triangles are similar using just one theorem, and then show 2 of them are similar using another. So we're going to have to kind of think about what we want to do. So over here, I'm going to find that missing piece. So if I add 47 and 29 together, I get 76. And so 180 minus 76 is going to give me the measure of angle C. So when I find that, I get it to be 104 degrees. So if this is 104 and this is 29, we can automatically assume this is 47. And then if this is 47 and 104, I can assume that this is 29 degrees. So right away, I can say that all 3 of these triangles are in fact similar. But I need to use 2 different theorems later on. So show that all 3 triangles are similar using one theorem. So triangle ABC, so I went from the 47 to the 29 to the 104. I'm going to do that again here. ABC is similar to triangle FED, which is similar to triangle, so 47, 29, 104, 47, 29, 104. So that would be GIH. And that's by angle-angle similarity. And notice I put the squiggle at the end to denote similarity. So that helps us with the first one. Now I need to look at showing 2 are similar using another theorem. Well, this one doesn't have any information about side lengths, but this one and this one do. So I'm going to have to prove that triangle ABC and triangle GHI in some order are in fact similar. So if I compare 4 to 2 and 6 to 3 and 8 to 4, I get all 2's. So that tells me that triangle ABC is similar. So I did A, B, C. So I did the long side and then the medium side. So long side and medium side would be GIH, and that would be by side, side, side similarity. And I can't prove that this one in the middle, DFE or DEF, is similar because we don't have any information about the side lengths. Now go ahead and try example 3 on your own. Okay, so I solved this 3 different ways. First, I needed to make these 2 triangles in this order similar. So I corresponded to figure out which pieces were corresponding. So AB relates to DE, so I highlighted that in green. BC corresponds to EF, so that's in purple, and then AC and DF correspond, so those are in blue. So I knew that these proportions had to follow true, and so I solved it 3 different ways depending on how you did it. You could have looked at the first 2, set them equal to each other, so I just reduced 4/12 to 1/3, and I got 7. As my final answer, I did the same thing if I did the first, so if I really did the green and purple is what I did first, then I did green and blue second, and then I did purple and blue third. And that one was probably a little bit more complicated just because it did become a quadratic, but you'll notice that I did get 7 every single time. Okay, and the last way to show that triangles are similar is by angle side similarity. So if an angle in one triangle is congruent to an angle of a second triangle, and the lengths of the sides that makes up those angles, if they're in proportion, then the triangles are similar. So if you look over here, you'll see that if we're talking about angle A and angle D, then the sides I need to look at are AC, AB, and DF, and DE. And so if I show that all of those 3 pieces are similar, so the angles have to be congruent, sides have to be within proportional, then the triangles are similar. So if we look over here, we're going to look at proving triangle ABC is similar to triangle ADE. So if it helps you to draw them separate, please do so. So if we do that first, so if I have triangle ABC, I notice that that side AC is made up of all of that. So that side would be 12, and I see this whole side would be 8. And then I have my little one in here, which is 9 and 6. And I have angle A, D, and E, and I see that both of these angles include angle A. Both triangles include angle A. So I have enough information to look at angle side similarity. So I know that angle CAB, so CAB is congruent to, so if you remember, congruent has the squiggle line on top and then an equal sign, angle EAD. So I have my angle already, and now we have to look at our sides. So that's congruent. Does 12/9, does that equal to 8/6? Well, 12/9 would reduce to 4/3, and 8/6 would also reduce to 4/3. So I have my angle in between the 2 sides that are in proportion. So triangle ABC is similar to triangle ADE by angle side similarity. Okay, so the last 2 things here are application problems. I want you to go ahead and try them first. So go ahead and pause this, try to go through them, and then I'll go through them quickly afterwards. Okay, so here are the 2 problems worked out. So I see that I have a little triangle here. This says it's angle R. I have a bigger triangle here. This is also angle R. And so I can see that if the mirror is right here where these 2 come together, these angles are the same. And I'm told that the person is 3 meters tall. I'm just going to say that I read that as 2 because the picture here shows that it's 2. So if you used 3, your answer will be slightly different than mine. So if he's 2 meters tall, 3 feet away, and then the meter is 21 meters away from the telephone pole, how tall? And so I just set up a simple proportion. Once I was able to show that the triangles are similar by angle similarity, I knew that these 2 were the same and they both had right angles. And so I cross-multiplied, solved, and I got 14 meters tall for the telephone pole. And then lastly for this one, I didn't write it out, but I knew that the triangles were similar by angle similarity again, because I see that they both share this angle where the other surveyor is, and so I just marked that with 2 lines. We both have right angles here, and so I was able to set up a proportion and solve and get 187.5 feet tall. So like I said before, we will do these 2 proofs when we get back together next week, but let me know if you have any questions.